Picture this: a swirling storm twice the size of Earth, raging for centuries in the atmosphere of a planet so massive it could swallow every other world in our solar system. Jupiter isn't just another dot in the night sky, it's a cosmic enigma, a gas giant hiding secrets that defy everything we think we know about the universe. What if the answers to some of astronomy's biggest questions, how planets form, whether life exists beyond Earth, even the fate of our own solar system, are locked within its turbulent clouds? For centuries, Jupiter has captivated scientists and stargazers alike. Its great red spot, a storm older than the United States, is just the beginning. This planet is a world of extremes where lightning strikes 1,000 times more powerful than Earth's illuminate skies, where winds scream at speeds faster than a bullet, and where mysterious auroras flicker in colors we can't fully explain. But here's the thing: every time we think we've figured Jupiter out, it surprises us again. Beneath its colorful bands of gas lie puzzles that challenge our understanding of physics, chemistry, and even the origins of life itself. Today we're diving deep into 25 of Jupiter's most baffling mysteries, phenomena so strange they seem ripped from science fiction. From hidden oceans beneath its moon's icy shells to bizarre magnetic fields that shouldn't exist, each discovery pulls back another layer of this planetary giant's secrets. Some of these mysteries might hold the key to finding life beyond Earth, others could reveal how our solar system was born, and a few, well, they might just rewrite the rules of the cosmos. So buckle up, we're about to explore a world where the impossible feels ordinary, and every answer leads to a bigger question. By the end, you'll never look at Jupiter the same way again. Imagine a hurricane so vast it could swallow our entire planet whole, and then keep raging for hundreds of years without slowing down. That's Jupiter's great red spot, a tempest of unimaginable power that has fascinated astronomers since the 1600s. This swirling vortex of crimson clouds stretches over 10,000 miles wide, dwarfing any storm Earth has ever seen, but what keeps it churning for centuries, defying all the laws that make storms on our planet fade within days or weeks. Scientists believe the secret lies in Jupiter's alien atmosphere. Unlike Earth, where storms feed off warm ocean waters before weakening over land, Jupiter has no solid surface to disrupt its winds. The Great Red Spot acts like a giant atmospheric wheel, spinning between two powerful jet streams that push it in opposite directions, essentially giving it an endless source of energy. And here's something even stranger: the storm isn't just surviving, it's changing. Recent observations show the spot shrinking, its once oval shape turning more circular, while its signature red hue has deepened into a richer, almost burnt orange color. Some researchers think these shifts could hint at hidden dynamics deep beneath Jupiter's clouds, where temperatures and pressures reach extremes we can barely replicate in labs. Then there's the mystery of its color. Why red on Earth? Rust gives Mars its reddish tint, but Jupiter's atmosphere is mostly hydrogen and helium, elements that shouldn't produce such vivid tones. One leading theory suggests ultraviolet radiation from the sun breaks down chemicals like ammonia or hydrogen sulfide in the upper atmosphere, creating complex compounds that glow crimson. Others speculate the storm dredges up mysterious materials from Jupiter's unseen depths, substances that react dramatically when exposed to sunlight. Every time we point a telescope or a spacecraft like Juno at this ancient maelstrom, it seems to reveal another layer of questions, perhaps the most unsettling possibility. The Great Red Spot might not be eternal. Measurements over the past century show it steadily shrinking, leading some scientists to wonder if we're witnessing the slow death of a solar system icon. Or maybe it's just evolving into something new, a storm we don't yet understand. One thing's certain: as long as this crimson whirlpool spins in Jupiter's skies, it will keep challenging everything we thought we knew about weather, planetary science, and the forces that shape our cosmic neighborhood. Jupiter should have a solid core, at least that's what every planetary formation model told us. When NASA Juno spacecraft arrived to peer beneath the planet's stormy exterior, scientists expected to find a dense, rocky heart, similar to Earth's but scaled up to match Jupiter's colossal size. Instead, the data revealed something far stranger, a core that's either partially dissolved, wildly uneven, or possibly missing altogether. This isn't just a minor discrepancy, it's a cosmic anomaly that forces us to rethink how giant planets are born. One theory suggests Jupiter once had a traditional core, but over billions of years, the unimaginable pressures and temperatures at its center, reaching tens of thousands of degrees, literally vaporized it, turning rock and metal into a soupy, diluted mixture suspended in the surrounding hydrogen. Picture a sugar cube dissolving in a cup of scalding tea, but on a planetary scale. If true, this would mean Jupiter's core isn't gone, it's just been smeared across the planet's interior, blending into the churning sea of metallic hydrogen that powers its monstrous magnetic field. But there's another, even more radical idea. What if Jupiter never had a solid core to begin with? Some scientists argue the planet might have formed directly from a collapsing cloud of gas, skipping the step where dust and debris clump together into a rocky center. This coreless model would upend our understanding of planetary birth, implying gas giants can assemble in ways we've never observed. Supporting this, Juno found traces of heavier elements scattered throughout Jupiter's atmosphere, as if the planet slurped up asteroids and comets haphazardly during its formation, never consolidating them into a neat, central core. The implications ripple far beyond Jupiter. If giant planets don't need solid cores, then our current methods for detecting exoplanets, which often rely on assumptions about their structure, might be flawed. Worse, it could mean we've misjudged the very recipe for how planetary systems, including our own, take shape. Every time Juno beams back new data, the mystery deepens, leaving us with more questions than answers. One thing's clear, Jupiter's missing core isn't just a puzzle, it's a paradigm shift waiting to happen. While Jupiter's great red spot steals the spotlight, its North Pole hides an even more perplexing spectacle, a perfect hexagon of clouds spinning with unnatural precision. This six-sided hurricane, stretching wider than Earth, looks like something out of geometry class rather than nature. Saturn has a similar formation, but Jupiter's version is far more chaotic, with turbulent jets screaming along its edges at 300 miles per hour. What cosmic force could carve such crisp angles into a planet where everything else swirls in organic curves? Unlike Earth's polar vortices, loopy wind patterns that come and go with seasons, Jupiter's hexagon appears locked in place, maintaining its shape for decades despite the planet's violent weather. One theory suggests powerful jet streams moving at different speeds create standing atmospheric waves, much like how blowing across a bottle's mouth produces musical notes. On Jupiter, these notes might resonate at frequencies that sculpt the clouds into geometric shapes. Another idea points to deep-rooted convection currents rising from Jupiter's interior, creating stable zones where storms self-organize into polygons. The strangest detail, this hexagon isn't alone. NASA Juno spacecraft revealed a family of 8 cyclones arranged in an octagonal pattern around it, like a celestial crown. While Saturn's North Pole hexagon stands solitary, Jupiter's version seems to be part of an intricate polar weather system we've never seen elsewhere in the solar system. Some researchers think these structures could be windows into Jupiter's hidden depths, surface manifestations of deep energy flows, and rotating layers of metallic hydrogen we can't directly observe. Why the difference between Jupiter and Saturn? Saturn's hexagon is cleaner, more symmetrical, possibly because its atmosphere lacks Jupiter's extreme turbulence and temperature variations. Jupiter's version appears messier, with tendrils of ammonia ice clouds leaking from its edges, as if struggling to maintain its shape against the planet's relentless churning. This contrast suggests that while both giants share hexagonal features, the underlying physics might be wildly different, a clue that planetary atmospheres operate by rules we're only beginning to decipher. Every time we study these alien geometries, they remind us that the universe often favors patterns far beyond our earthly experience. Lightning on Earth follows a simple recipe: water vapor rises, creates turbulent storms, and generates electrical discharges. But Jupiter laughs in the face of earthly logic. Here, bolts of lightning crackle through clouds with little to no water vapor, a phenomenon that defies every textbook explanation. These aren't just sparks, they're monsters, packing up to 3 times the energy of our most powerful superbolts. And the strangest part, ammonia, a gas we associate with cleaning products, might be the secret ingredient fueling these alien tempests. Jupiter's thunderstorms brew in frigid cloud decks where temperatures plunge to -100 degrees Fahrenheit, far too cold for liquid water to exist in abundance. Instead, scientists believe ammonia acts like an antifreeze, mixing with trace amounts of water to form a slushy, electrically conductive cocktail. When this slush gets tossed around by Jupiter's supersonic winds, it generates charges strong enough to ignite lightning, some flashes so vast they'd span entire continents on Earth. NASA Juno spacecraft has eavesdropped on these discharges, capturing radio bursts that sound like eerie, popping static, as if the planet itself is whispering secrets in a language of electricity. The scale is mind-bending. While Earth's lightning might stretch a few miles, Jupiter's bolts can arc over hundreds of miles, illuminating storms larger than our planet. Some even erupt high above the cloud tops, where the atmosphere is too thin for traditional lightning, a puzzle that hints at exotic charging mechanisms we've yet to unravel. One theory suggests ice-coated ammonia crystals collide in the upper atmosphere, creating friction so intense it rips electrons loose. Another proposes metallic hydrogen deeper down, swirling in Jupiter's interior, generates currents that surge upward like a cosmic battery. What's clear is this: Jupiter's lightning isn't just a scaled-up version of ours. It's a radical departure, proving that nature can invent entirely new ways to unleash energy when handed different ingredients. Every crackle recorded by Juno forces us to rewrite the rules, reminding us that even the most familiar phenomena, like a flash of lightning, can become alien on a world that plays by its own physics. Jupiter's magnetic field shouldn't look like this. In most planets, these invisible force fields wrap symmetrically around the world, like the neat lines around a child's toy magnet. But Jupiter's magnetism is lopsided, a chaotic, off-kilter mess where the northern hemisphere bristles with twice the strength of the south. This isn't just a minor irregularity, it's a fundamental challenge to dynamo theory, the foundational science explaining how planets generate magnetic fields through the motion of conductive fluids deep inside them. If Jupiter's field defies the rules, what does that mean for our understanding of planetary cores across the galaxy? One clue lies in the Great Blue Spot, an oddly named but critical feature near Jupiter's equator. Unlike its famous crimson cousin, this isn't a storm, it's a concentrated knot of magnetic energy, a swirling vortex of invisible forces where field lines bunch together like tangled wires. Data from NASA Juno mission reveals this spot is ground zero for Jupiter's magnetic weirdness, acting like a cosmic thumb pressing down on the planet's electromagnetic fabric. Scientists suspect it's linked to deep currents within Jupiter's ocean of metallic hydrogen, where pressures are so intense that hydrogen behaves like a liquid metal, conducting electricity and amplifying magnetism in ways we've never seen on Earth. The asymmetry might trace back to Jupiter's missing or smeared core. Without a solid, symmetrical anchor at its heart, the dynamo churning out the magnetic field could be uneven, with turbulence in the northern hemisphere generating stronger fields than the south. Alternatively, Jupiter's rapid rotation, spinning once every 10 hours, might twist and stretch the magnetic lines asymmetrically, like a taffy puller working faster on one side. Some researchers even propose that Jupiter's interior is layered like an onion, with different zones of conductive material rotating at varying speeds, creating patches of intense magnetism. What's undeniable is the ripple effect of this discovery. Magnetic fields act as cosmic shields, deflecting harmful solar radiation. If Jupiter's lopsided field leaves certain regions more exposed, it could explain why some of its moons, like Europa, show strange patterns of radiation damage. Even more intriguing, exoplanet hunters often assume distant gas giants have symmetrical magnetic fields. If Jupiter's imbalance is common, we might need to rethink how habitable or hostile alien worlds truly are. Every new measurement from Juno peels back another layer of this magnetic mystery, proving that even the most familiar cosmic forces can surprise us when we look closely enough. When you picture planetary rings, Saturn's dazzling icy bands probably come to mind, but Jupiter's rings are the solar system's best-kept secret. Unlike Saturn's brilliant, reflective hoops, Jupiter's are ghostly, made of fine dust so dark they weren't even discovered until Voyager 1 swung by in 1879. These ethereal loops are so faint, they'd disappear if you stood on Jupiter's cloud tops and looked up. So how does the solar system's largest planet end up with such underwhelming rings? The answer lies in a cosmic demolition derby happening right above our heads. Jupiter's rings are fed by violence. Micrometeoroid space debris no larger than grains of sand constantly pummel the planet's 4 inner moons, especially tiny Medes and Adrastea. Each impact kicks up plumes of dust, scattering particles into orbit like flour tossed into a fan. Without this endless bombardment, Jupiter's rings would vanish within years, as solar radiation and magnetic fields slowly drag the dust away. It's a delicate balance. Too few impacts and the rings fade, too many and they'd grow thicker. Right now, Jupiter sits in a Goldilocks zone of destruction, maintaining rings just dense enough to exist but too thin to shine. Here's where it gets bizarre. Saturn's iconic rings are mostly ice, reflecting sunlight like a cosmic mirror. Jupiter's, by contrast, are built from dark, rocky material, likely pulverized remnants of ancient asteroids, or even volcanic ash from Io. This explains their eerie transparency. They absorb light instead of bouncing it back. Side by side, the difference is staggering. If Saturn's rings are a neon sign, Jupiter's are a shadow puppet show. Yet these faint loops hold clues to Jupiter's violent history. Some scientists believe they're temporary, the aftermath of a moon shattered by a colossal collision. Others argue they've been steadily replenished for billions of years, a slow-motion ballet of destruction and renewal. The real mystery: why some gas giants get icy, dazzling rings while others settle for dusty whispers. Saturn's might come from a torn-apart moon or captured comet, while Jupiter's seem more like a byproduct of its messy orbital neighborhood. One theory suggests Saturn's gravity shepherds ice into orderly rings, while Jupiter's immense magnetic field grinds debris into fine powder. Whatever the reason, Jupiter's ghostly rings remind us that even the most subtle features in space can tell explosive stories, if we know how to look. Beneath Europa's cracked, icy shell lies an ocean so vast, it holds more liquid water than all of Earth's seas combined, a dark, alien abyss locked under miles of frozen crust. This isn't just water, it's a potential haven for life, warmed not by sunlight but by the relentless gravitational tug of war between Jupiter and its moons. Every time Europa flexes in its orbit, friction generates enough heat to keep this subsurface sea from freezing solid. But what's truly staggering are the hints that this ocean might occasionally erupt into space, sending plumes of water vapor hundreds of miles high, a discovery that turned this icy moon into one of the most promising places to search for extraterrestrial life. The first clues came from Hubble Space Telescope observations in 2012, when astronomers spotted what looked like faint, finger-like projections near Europa's south pole. These weren't static features, they flickered in and out of view, suggesting sporadic geysers punching through the ice. Later observations caught similar plumes in 2016 and 2019, some reaching over 100 miles high. But here's the puzzle: are these genuine water jets or something more exotic? Some scientists argue these could be volcanoes, eruptions of slushy ice and brine, rather than pure water vapor. Others propose tidal forces might crack Europa's ice temporarily, allowing underground water to escape like steam from a pressure cooker before the fractures reseal. What makes these plumes so tantalizing is what they carry. If Europa's ocean contains the chemical building blocks of life, hydrothermal vents, organic molecules, or even microbial organisms, these eruptions could be spraying that material directly into space, where spacecraft might sample it without needing to drill through miles of ice. That's exactly what NASA Europa Clipper mission, launching in 2024, aims to do. Flying through these plumes with instruments far more sensitive than Hubble's, it could analyze their chemistry in real time, searching for amino acids, lipids, or other biomarkers. Even more audacious, some researchers have proposed a lander that could touch down near fresh plume deposits, tasting the ice for signs of biology. The implications are staggering. If life thrives in Europa's sunless ocean, it would prove that life can arise in environments we once thought impossible, opening the door to similar oceans hidden within icy moons like Enceladus or Ganymede. But Europa's ocean is no gentle pond. Crushed under immense pressure, bombarded by Jupiter's radiation, and potentially laced with toxic compounds, it would demand organisms unlike anything on Earth. Yet extremophiles in our own deep-sea vents prove life clings on in the harshest places. Whether Europa's plumes are geysers or cryovolcanoes, they're more than just cosmic curiosities. They're messengers from an alien sea, and we're finally learning how to listen. If Earth's volcanoes seem impressive, Io makes them look like flickering birthday candles. Jupiter's innermost large moon is a hellish puzzle, erupting with hundreds of active volcanoes that paint its surface in sulfur-specked yellows and fiery oranges. Thermal images reveal a landscape so volatile that some lava flows stretch hundreds of miles, their temperatures hot enough to melt steel. But what transforms this tiny world, just slightly larger than Earth's moon, into the most geologically violent place we've ever seen? The answer lies in an endless gravitational tug-of-war. Io pays a brutal price for its orbit around Jupiter. Squeezed between the gas giant's immense gravity and the competing pulls of neighboring moons Europa and Ganymede, Io's interior gets stretched and compressed like taffy. This tidal heating generates more energy than all of Earth's nuclear reactors combined, liquefying rock beneath the crust and fueling non-stop eruptions. Some plumes blast material 200 miles into space, so high that particles escape Io entirely, feeding a donut-shaped cloud of charged atoms around Jupiter itself. The scale is incomprehensible. Io pumps out 100 times more lava each year than all of Earth's volcanoes combined, constantly repaving its surface in a cycle of destruction and rebirth. Yet the strangeness runs deeper. Io's lava isn't like ours. Earth's eruptions typically spew basalt, a thick, slow-moving melt rich in silica, but Io's superheated flows resemble ancient cometite, an ultramafic lava so runny it might resemble water gushing from fractures. This suggests Io's interior is far hotter and more primitive than Earth's, with magma reservoirs reaching temperatures around 2000 degrees Fahrenheit. Some volcanoes, like Lopsided, behave like nothing on our planet. This 80-mile-wide lava lake acts more like a periodically erupting cauldron, its crust overturning every few years in waves of molten rock visible from orbit. The implications stretch beyond our solar system. If tidal forces can turn a small moon into a volcanic inferno, what might they do to exoplanets orbiting close to gas giants? Io challenges our assumptions about where geological activity and maybe even life could exist. Its eruptions prove that heat doesn't always come from starlight or radioactive decay. Sometimes it's written in the invisible push and pull between celestial neighbors. As Jupiter's gravity needs Io daily, this tortured moon reminds us that even in the coldest reaches of space, fire finds a way. Ganymede isn't just Jupiter's largest moon, it's a solar system oddity with secrets that blur the line between moon and planet. Beneath its icy, cratered surface lies a liquid ocean so deep it could drown Earth's tallest mountains, while overhead, its own magnetic field flickers like a miniature version of Jupiter's. No other moon in our solar system boasts this combination, making Ganymede a cosmic rebel with two groundbreaking mysteries: an underground sea that might harbor life, and a magnetic personality that shouldn't exist. Let's start with the ocean. Hidden under 95 miles of ice, Ganymede's subsurface water isn't just a puddle, it's a sprawling abyss, holding more liquid than all of Earth's oceans combined. But unlike Europa's ocean, which stays liquid thanks to tidal heating, Ganymede's secret sea defies expectations. Here, the heat comes from within. Radioactive decay in Ganymede's rocky core warms the water, while immense pressure from the overlying ice keeps it from freezing solid. Even stranger, this ocean isn't uniform. Scientists suspect it's layered like a cosmic parfait, with slushy ice shelves floating between zones of liquid and even denser, saltier water pooling at the bottom. That salt could be the key to habitability. On Earth, extremophiles thrive in briny environments. Could Ganymede's dark, pressurized depths host similar life? Then there's Ganymede's magnetic field, a feature no other moon possesses. Generated by churning molten iron in its core, this field wraps the moon in an invisible shield, interacting violently with Jupiter's far stronger magnetism. The result: auroras unlike anything in our solar system. While Earth's northern lights dance in thin air, Ganymede's auroras are locked in a tug of war, their ribbons of glowing plasma squeezed into double arcs by Jupiter's overpowering influence. NASA Hubble telescope has spotted these eerie lights. Their glow fueled not by solar wind, but by particles stolen from Jupiter's own magnetic bubble. The most baffling part: Ganymede's field shouldn't last. Small bodies like moons usually lose their internal heat, and thus their magnetic dynamos billions of years ago. Yet Ganymede still churns, suggesting either a freakishly long-lived hot core or an unseen energy source. Some theories point to tidal forces from Jupiter, subtly kneading Ganymede's interior like cosmic hands warming clay. Others propose that the moon's core is layered, with a solid inner heart surrounded by a molten outer shell, creating a self-sustaining geodynamo. Whatever the cause, this tiny magnetic field punches far above its weight, carving a protective bubble within Jupiter's radiation-heavy domain. What does this mean for life? A magnetic field could shield Ganymede's ocean from Jupiter's lethal radiation, making its depths one of the most promising places to look for extraterrestrial microbes. But there's a catch: the ocean's layered structure might prevent vital nutrients from mixing, creating isolated pockets rather than a globally habitable zone. Upcoming missions like ESA's JUICE probe aim to solve these puzzles, mapping Ganymede's hidden waters and magnetic quirks in unprecedented detail. One thing's certain: this moon isn't just a frozen rock. It's a dynamic world with liquid, light, and magnetism, a place where the rules of planetary science get rewritten. Callisto stands as a silent rebel among Jupiter's moons, a world frozen in time. While its siblings Io, Europa, and Ganymede churn with volcanic fury or hide global oceans, Callisto's surface is a scarred relic of the solar system's violent youth. Pockmarked by more craters than any other body we've seen, it looks like a cosmic punching bag that's taken billions of years of hits without flinching. But here's the puzzle: why is Callisto so eerily still when its neighbors are seething with geological drama? The answer might rewrite what we know about moon formation and the hidden forces shaping our cosmic backyard. Unlike Europa and Ganymede, Callisto shows no signs of tidal heating, the gravitational kneading that fuels their subsurface oceans and volcanic tantrums. Orbiting farther from Jupiter, It avoids the intense gravitational tug of war that stirs its siblings' interiors, but distance alone doesn't explain everything. Saturn's moon Enceladus, also relatively distant, erupts with icy geysers thanks to orbital resonances. Callisto, by contrast, seems locked in a quiet harmony with Jupiter, untouched by the chaotic dances that heat other moons. Some scientists call it a dead moon, but that label might sell it short. Its stillness could be the key to unlocking secrets older than the planets themselves. Peer closely at Callisto's battered face and you'll spot something astonishing: craters on top of craters layered like rings in a tree trunk. The largest, Valhalla Basin, spans nearly 2,000 miles, a bullseye of concentric fractures from an impact so ancient it likely happened before Earth's oceans formed. What's shocking is how little these scars have eroded. Without volcanic resurfacing or tectonic activity, Callisto's craters remain pristine, offering a fossilized record of the solar system's most violent era. This makes it a time capsule, preserving clues about the bombardment that shaped all planetary surfaces, including Earth's. Beneath this battered exterior lies another enigma, a possible liquid ocean, detected by subtle wobbles in Callisto's magnetic field. Unlike Europa's or Ganymede's oceans, this one isn't kept warm by tidal forces. Instead, radioactivity or leftover heat from Callisto's formation might maintain it, a faint whisper of warmth in an otherwise frozen world. If confirmed, it would prove that liquid water can exist in the unlikeliest places, without the dramatic energy sources we once thought necessary. Callisto's contradictions force us to rethink what makes a moon alive. Its surface is dead by geological standards, yet it might harbor a secret sea. It's battered yet unchanged, ancient yet potentially dynamic. For astronomers, it's a reminder that sometimes the quietest worlds hold the loudest truths about how planetary systems evolve. While flashier moons steal headlines, Callisto waits patiently, a dusty archive of cosmic history, daring us to decode its silence. Jupiter's atmosphere doesn't just end where the clouds stop, it plunges into an abyss so deep it defies comprehension. Imagine diving into an ocean where the pressure doesn't just crush submarines, it transforms hydrogen itself into a shimmering, metallic liquid. This isn't science fiction, it's the reality lurking beneath Jupiter's colorful bands, where the gases we think we know behave in ways that rewrite the laws of physics. The challenge is that no spacecraft, not even NASA Juno probe, can peer directly into this alien realm. Jupiter's cloud tops, those swirling stripes of ammonia and water vapor, act like a cosmic veil, hiding the chaos below. Juno's instruments measure magnetic fields, gravity, and microwave emissions, painting an indirect picture of the turmoil beneath. What they've revealed is staggering: an atmosphere stretching tens of thousands of miles downward, where temperatures soar to thousands of degrees and pressures reach millions of times Earth's sea level. At these extremes, hydrogen, the lightest element in the universe, gets squeezed so tightly its electrons break free, forming a bizarre metallic soup capable of conducting electricity like copper. This metallic hydrogen layer isn't just a curiosity, it's the engine behind Jupiter's monstrous magnetic field, the strongest in the solar system after the Sun's. But here's the twist: scientists still debate whether this layer is uniform or a churning, turbulent sea with currents we can't yet map. Some theories suggest it might even rain helium here, droplets of the gas condensing and falling like diamonds through the metallic hydrogen, releasing heat as they descend. Other models propose vast, rotating cylinders of gas, deeper still, acting like planetary scale gears driving Jupiter's jet streams above. The deeper you go, the stranger it gets. Near the core, if Jupiter even has a traditional one, pressures could exceed 40 million times Earth's atmosphere, creating conditions so extreme that hydrogen might exist in phases we've never replicated in labs. Some researchers speculate about exotic quantum behaviors or even superfluidity, where fluids flow without friction. It's a realm where our understanding of matter itself breaks down, leaving us with more questions than answers. Juno's greatest revelation might be how little we truly know. Every pass over Jupiter's poles or scan of its gravity field adds another puzzle piece, but the full picture remains maddeningly out of reach. What's clear is this: Jupiter's atmosphere isn't just a layer of gas, it's a dynamic, multi-tiered hellscape where familiar elements become alien, and the rules of chemistry and physics bend under pressures we can barely fathom. Until we send a probe brave enough to dive deeper, the secrets of Jupiter's abyss will stay locked behind that swirling, stormy veil. Jupiter should be soaked in water, at least that's what every model of the solar system's formation tells us. When the planets were born, oxygen was the third most abundant element, meaning Jupiter's atmosphere ought to be brimming with H2O, yet when NASA Juno spacecraft trained its microwave radiometer on the planet's cloud tops, it found a desert where oceans should be. The upper layers of Jupiter's swirling storms are startlingly dry, with water levels up to 10 times scarcer than expected. This isn't just a discrepancy, it's a cosmic whodunit that challenges our understanding of how giant planets form and evolve. The mystery deepens when you consider Jupiter's composition. The planet's colorful bands are rich in ammonia and hydrogen sulfide, but water, the molecule that dominates chemistry everywhere else in the solar system, is conspicuously absent from the mix. One theory suggests Jupiter's water isn't missing, it's just hiding. Powerful downdrafts in the atmosphere might be dragging moisture far below the visible cloud decks, sequestering it in layers where Juno's instruments can't easily detect it. Imagine a planetary-scale elevator, shuttling water vapor downward into a realm where pressures crush it into exotic forms like supersonic ice, a state where water acts as both solid and liquid simultaneously. Juno's microwave experiments offer intriguing clues. By measuring thermal radiation emitted from deep within Jupiter's atmosphere, the spacecraft detected sporadic pockets where water concentrations spike. These wet zones aren't evenly distributed, they're clustered near the equator and under massive storm systems, like the Great Red Spot. It's as if Jupiter's weather acts like a giant blender, occasionally churning up buried moisture from below. Some scientists compare it to Earth's ocean currents, which sometimes bring deep, cold water to the surface in localized upwellings only on Jupiter. The currents are supersonic jet streams, and the water might be mixed with molten minerals. The stakes are higher than just solving a planetary puzzle. Water is a universal solvent, a key ingredient for life as we know it, and a critical factor in how gas giants regulate their heat and weather. If Jupiter's water is locked away in its depths, it could mean the planet formed differently than we assumed, perhaps accreting drier material than expected, or losing its water early in a violent phase of solar system history. Worse, it might imply our models for exoplanets are flawed, since astronomers often use Jupiter as a template for guessing the composition of distant gas giants. The answer could lie in Juno's next plunge over Jupiter's poles, where strange cyclones swirl in geometric patterns, or it might require a future probe brave enough to dive deeper, sniffing out water in the planet's forbidden layers. Until then, Jupiter's missing water remains a ghost in the data, a whisper of something fundamental we're still learning how to see. While Earth's auroras paint delicate green ribbons across polar skies, Jupiter's light shows are something else entirely, a relentless, cosmic fireworks display fueled by forces we're still struggling to comprehend. These aren't just pretty lights, they're monster versions of our own northern and southern lights, burning hundreds of times brighter and spanning areas larger than Earth itself. And here's what makes them truly alien: they never stop. Earth's auroras flicker during solar storms, but Jupiter's blaze around the clock, powered not by the sun, but by its own moons and a magnetic field so intense, it turns the space around it into a particle accelerator. The energy source is unlike anything in our solar system. On Earth, auroras ignite when solar wind particles collide with atmospheric gases. Jupiter, though too distant for solar wind to pack much punch, has a secret weapon: its volcanic moon Io. Every second Io spews a ton of sulfur and oxygen into space, creating a donut-shaped plasma cloud along its orbit. Jupiter's magnetic field snatches these charged particles, whipping them toward the poles at near light speed. When these particles slam into hydrogen molecules in Jupiter's upper atmosphere, they unleash ultraviolet and X-ray auroras so powerful they'd be lethal to any nearby life. The X-rays alone carry enough energy to heat Jupiter's upper atmosphere to thousands of degrees, a phenomenon scientists still can't fully explain. Then there's the location puzzle. Earth's auroras hug polar circles, but Jupiter's erupt in unexpected places, sometimes even near the equator. NASA Juno spacecraft revealed patches of auroral activity far from the poles, defying models that assumed Jupiter's magnetic field would funnel particles uniformly to the poles. One theory suggests chaotic magnetic interactions between Jupiter and its moons create leaks in the system, scattering energized particles across latitudes. Another points to Jupiter's lopsided magnetic field, which might redirect particles along unpredictable paths. The most baffling detail, Jupiter's main auroral rings, while centered on the poles, aren't symmetrical. The northern aurora pulses differently than the southern one, as if the planet's magnetic engine is misfiring on one side. Some scientists think this ties back to Jupiter's mysterious inner workings, perhaps its uneven metallic hydrogen layer, or the Great Blue Spot's magnetic anomaly. Others speculate that Ganymede's independent magnetic field disrupts Jupiter's particle flows, adding another layer of complexity. What's certain is this: Jupiter's auroras aren't just scaled-up versions of Earth's. They're a window into the violent, invisible forces shaping the Jovian system, a reminder that even the most familiar cosmic phenomena can take on radical new forms when the rules of physics get rewritten by a planet that plays by its own playbook. Every flicker of these eternal lights carries coded messages about Jupiter's interior, its moons, and the electrified dance between them. Deep in Jupiter's polar skies, a cosmic strobe light flashes with bizarre precision, bursts of X-rays so powerful they outshine the planet's already dazzling auroras. Unlike Earth's gentle northern lights, these flares pack the energy of volcanic eruptions, pulsing like clockwork every 27 minutes at the North Pole and every 45 minutes at the South. NASA Chandra X-ray Observatory first spotted this rhythmic light show in 2007, but 2 decades later, we're still scratching our heads over what could possibly power such punctual, high-energy explosions on a planet with no solid surface. The strangest part, these X-rays seem to dance to the solar wind's tune. When gusts of charged particles from the Sun buffet Jupiter's magnetic field, the X-ray flares intensify, as if the planet is absorbing that energy and transforming it into something far more violent. But here's where the mystery deepens. Jupiter's own volcanic moon Io also seems to play a role. The same donut-shaped plasma cloud that fuels Jupiter's auroras might be feeding these X-ray pulses too, creating a feedback loop where particles get accelerated to near light speed before slamming back into the planet's atmosphere. It's like a cosmic particle accelerator built into the planet's magnetic scaffolding, one we didn't know existed until Chandra's detectors caught it in action. Then there's the timing puzzle. Why 27 and 45 minutes? On Earth, natural phenomena rarely obey such precise intervals unless tied to rotation or orbital mechanics. But Jupiter's X-ray pulses don't match its 10-hour spin or any known cycle of its moons. Some researchers think magnetic waves rippling through Jupiter's polar regions could be acting like pendulums, swinging charged particles back and forth with clockwork regularity. Others suggest these pulses might trace back to resonant frequencies in Jupiter's magnetosphere, echoes of some deeper, unseen process churning in the metallic hydrogen ocean below. Chandra's latest observations add another twist. The North and South Pole flares don't sync up. While both pulse steadily, they operate on independent schedules, as if Jupiter's hemispheres are running on different cosmic metronomes. This asymmetry hints at cracks in our understanding of how planetary magnetic fields distribute energy. If Jupiter's lopsided core or turbulent interior is skewing these emissions, it could mean gas giants generate and release energy in ways our physics can't yet model. What's at stake isn't just a Jovian curiosity. X-ray flares like these could be common among exoplanets, especially gas giants orbiting close to their stars. If so, they might serve as invisible beacon signatures of magnetic activity that telescopes could detect across light years. But first, we need to decode why Jupiter, a planet 5 times farther from the Sun than Earth, produces X-rays fiercer than anything in our own backyard. Every flicker from those polar storms is a cipher, waiting for the right scientific key to unlock its secrets. For centuries, Jupiter's Great Red Spot has been the solar system's most enduring storm, a colossal hurricane that could swallow Earth twice over. But recent observations reveal something unsettling. This ancient tempest is shrinking, its once oval form tightening into a near-perfect circle, while its fiery hues deepen from brick red to burnt orange. Back in the 1800s, astronomers estimated the storm spanned 25,000 miles wide enough to fit 3 Earths side by side. Today, it measures barely 10,000 miles across, shrinking at a rate that could see it vanish entirely within our grandchildren's lifetimes. What cosmic forces are dismantling this iconic storm, and why is its color transforming before our eyes? The answers might rewrite how we understand planetary weather systems forever. One leading theory points to atmospheric cooling. Jupiter's upper clouds have been chilling over decades, possibly due to subtle shifts in sunlight absorption or changes in the planet's internal heat flow. As temperatures drop, the storm's energy supply drawn from warm gases rising from below might be starving, causing it to contract like a deflating balloon. Supporting this, infrared telescopes have spotted thinning cloud layers around the spot's edges, as if the storm is literally evaporating from the outside in. But here's the catch: if cooling alone were responsible, the spot should weaken uniformly. Instead, its winds have actually accelerated at the periphery, reaching speeds of 400 miles per hour faster than ever recorded. This suggests something far stranger is at work. The color shift adds another layer of mystery. The Great Red Spot signature hue has long been attributed to complex molecules called chromophores, which form when sunlight breaks down ammonia and hydrogen sulfide in the upper atmosphere. But as the storm shrinks, its deepening red tones hint at a more dramatic process. Some scientists believe the contraction is dredging up darker, sulfur-rich compounds from Jupiter's lower atmosphere, material usually hidden miles beneath the cloud tops. Others propose that the intensifying winds are concentrating these chemicals like a cosmic centrifuge, amplifying their color, the most radical theory. The spot might be ingesting smaller storms, absorbing their chemistry like a planetary scale predator. Time lapses from Hubble show mysterious dark blades, occasionally spiraling into the vortex, possibly delivering fresh pigments. The most tantalizing clue comes from Jupiter's deep interior. Juno's gravity measurements reveal massive planetary waves. Think of them as Jupiter's version of ocean tides rippling beneath the spot. These waves could be siphoning energy away from the storm or even altering how material rises from below. Imagine a boiling pot of water. If you shake the pot, the bubbles rise differently. Jupiter's internal turbulence might be doing the same to the spot's lifeblood, choking off its fuel supply in unpredictable ways. Whether the Great Red Spot is dying or simply evolving remains an open question. Some models suggest it could stabilize at a smaller size, while others predict total dissipation within decades. Its fate isn't just academic. This storm is a living laboratory for hypergiant weather systems, including those on exoplanets where winds might scream at thousands of miles per hour. As we watch this centuries-old tempest transform, we're witnessing more than just a storm's end. We're seeing a cosmic clock tick, counting down to the moment when Jupiter's most famous feature becomes just another footnote in astronomical history, unless, of course, it surprises us all and finds a way to outlast even our boldest predictions. High above Jupiter's churning clouds lies a layer of atmosphere so hot it defies every textbook, a region called the thermosphere where temperatures soar to over 1,000 degrees Fahrenheit, hotter than parts of Mercury despite being 5 times farther from the Sun. This isn't just a mild discrepancy, it's a full-blown cosmic furnace that has physicists scratching their heads. If sunlight alone can't explain this inferno, what invisible forces are cooking Jupiter's upper atmosphere to such extremes? The prime suspect, Jupiter's relentless auroras. While Earth's northern lights gently warm the upper atmosphere, Jupiter's auroras are more like atmospheric blowtorches, pumping enough energy into the thermosphere to melt steel. Charged particles, accelerated to near light speed by the planet's monstrous magnetic field, slam into hydrogen molecules with enough force to generate X-rays and ultraviolet radiation, heat sources so intense they can superheat entire regions. But here's the catch: models show these auroras, while powerful, shouldn't be enough to explain the thermosphere's planet-wide scorch. The heat should stay concentrated near the poles, yet it spills equatorward, wrapping Jupiter in a global heat blanket. That's where gravity waves enter the mystery. Unlike the gravitational waves from colliding black holes, these are rhythmic disturbances in Jupiter's atmosphere. Think of them as planetary scale vibrations. As storms rage below, they send shockwaves rippling upward, like ocean waves crashing against an invisible shore. When these waves break in the thin upper atmosphere, they release energy as heat, potentially acting as a hidden heating system. Recent data from the Juno spacecraft hints at these waves propagating from deep storms, but the math still doesn't add up. The waves are too weak to account for the thermosphere's blistering temperatures, leaving scientists to wonder if Jupiter's interior is secretly funneling energy upward through mechanisms we haven't even imagined. Then there's the wildcard magnetospheric drag. Jupiter's rotation is so fast, it's spinning once every 10 hours, that its magnetic field can't quite keep up, creating a sort of cosmic friction between the planet and its own magnetosphere. This drag might generate electrical currents that dissipate as heat, like a gargantuan version of the warmth you feel when rubbing your hands together. Some researchers argue this process could be the missing piece, pumping energy into the upper atmosphere like an invisible space heater. The implications stretch beyond Jupiter. If we can't explain why a gas giant's upper atmosphere is hotter than logic allows, how accurate are our models for exoplanets? Many so-called hot Jupiters orbiting distant stars have even more baffling temperature profiles. Jupiter's thermosphere is a cosmic pressure test, revealing just how little we understand about energy transfer in alien atmospheres. Until we solve this puzzle, every textbook diagram of planetary heating might be missing a chapter, one written in the searing, invisible ink of Jupiter's skies. Jupiter's equator should be a sweltering belt of heat, basking in the sun more directly than its poles, but instead it's a cosmic contradiction. Infrared maps reveal a strange chill hugging the planet's midsection, with temperatures dipping hundreds of degrees colder than theoretical models predict. This isn't just a minor glitch in planetary science, it's a glaring anomaly that suggests something fundamental is missing from our understanding of how gas giants distribute heat. The culprit, a complex dance of jet streams and atmospheric waves that rewrite the rules of planetary meteorology. At first glance, Jupiter's equator seems like it should follow simple physics: sunlight strikes it head-on, so it should radiate warmth. But the planet's breakneck rotation throws a wrench into that logic. Spinning at nearly 28,000 miles per hour, Jupiter's equator whips around faster than its higher latitudes, creating violent eastward jet streams that act like atmospheric refrigerators. These supersonic winds, some exceeding 300 miles per hour, siphon heat away from the equator, dumping it toward the poles in a planetary scale redistribution system. Think of it like a ceiling fan set to maximum speed, chilling the room beneath it by constantly stirring the air, yet the jet streams alone can't explain the depth of the equatorial chill. Enter Jupiter's mysterious wave dynamics. High-resolution thermal images from telescopes like the Subaru Observatory show rippling temperature patterns, suggesting massive atmospheric waves similar to Earth's Rossby waves, but vastly larger, are actively cooling the region. These waves might propagate vertically, shunting warm gas upward where it radiates heat into space, or horizontally, like undulating conveyor belts ferrying warmth poleward. Some researchers even speculate that Jupiter's internal heat, seeping from its core, interacts destructively with solar heating at the equator, creating pockets of unexpected cold. The smoking gun might lie in ammonia distribution. Microwave scans reveal that Jupiter's equatorial zone is oddly depleted of this gas, which normally traps heat. Instead, powerful downdrafts seem to be plunging ammonia-rich air deep below the cloud tops, leaving behind a thinner, cooler layer. It's as if the planet is built in atmospheric vents at the equator, purposefully bleeding off heat. The result is a thermal map that looks more like a poorly wired heating system, hot spots near the poles, frosty patches at the equator, than anything nature should allow. This bizarre cooling has implications far beyond Jupiter. Exoplanet hunters often assume distant gas giants follow predictable temperature gradients, with equators warmer than poles. But if Jupiter, the archetypal gas giant, defies that rule, it could mean our models for alien worlds are built on flawed assumptions. Every new infrared scan of Jupiter's equator forces us to ask, are we seeing a unique quirk of our solar system, or a universal feature of giant planets that we've just begun to recognize? Until we decode this atmospheric puzzle, the cold equator stands as a stark reminder that even the most basic planetary traits can hide astonishing complexities. Jupiter's jet streams don't just break records, they shatter every expectation of how planetary weather should behave. Clocking speeds over 1,000 miles per hour, these monstrous rivers of gas whip around the planet faster than the winds inside a Category 5 hurricane, yet they've maintained their same basic patterns for centuries. On Earth, jet streams meander, split, and fade with the seasons. On Jupiter, they race along like perfectly greased tracks, their paths so stable they've barely budged since Galileo first sketched them in the 17th century. What gives this planet the power to sustain such relentless, orderly chaos? The secret lies in Jupiter's lack of a solid surface, a feature that turns conventional meteorology upside down. Earth's winds slow down when they collide with mountains or drag across oceans, but Jupiter's atmosphere has no such brakes. Instead, its jet streams are free to accelerate unimpeded, fueled by heat rising from the planet's scorching interior. Imagine a pot of water boiling on a stove. As hot fluid rises and cold fluid sinks, it creates circulating currents. Jupiter operates on the same principle, but scaled up to a planetary madness where the stove is a radioactive core and the pot is an atmosphere 13,000 miles deep. This constant churning, combined with Jupiter's dizzying rotation, spinning once every 10 hours, generates Coriolis forces so strong they shear the atmosphere into those iconic striped bands and hypercharged jets. But speed isn't the only puzzle. It's the jet's inexplicable stability that baffles scientists. Earth's weather is a turbulent mess because our planet's surface, with its continents and oceans, creates friction and temperature imbalances. Jupiter, by contrast, is a fluid dynamo with no landmasses to disrupt the flow. Its jet streams act like planetary gears, locked into place by a feedback loop where energy from the deep atmosphere reinforces the very winds that help distribute that energy. Some researchers compare it to a self-regulating engine. The faster the jets move, the more efficiently they transport heat, which in turn maintains the conditions that keep the jets running. The real wild card: Jupiter's jet streams might be thinner than we thought. Data from NASA Juno spacecraft suggests these supersonic winds could be confined to a relatively shallow layer, perhaps no deeper than 200 miles beneath the cloud tops. That raises even more questions. If the jets don't tap into Jupiter's deep energy reserves, what's preventing them from fizzling out? One theory points to thunderstorms, Jupiter's version of Earth's tropical cyclones, pumping energy upward like atmospheric pistons. Another proposes that magnetohydrodynamic effects, where Jupiter's magnetic field interacts with conductive layers of the atmosphere, act as an invisible stabilizer. What's certain is that these winds aren't just a Jovian oddity, they're a masterclass in fluid dynamics. By studying them, scientists hope to unlock secrets about atmospheric behavior on exoplanets, where winds might scream at even more extreme velocities. Jupiter's jet streams are more than cosmic speed demons. They're proof that when you remove the brakes from a planet's weather system, the results can defy everything we thought we knew about wind, storms, and the forces that shape alien skies. Jupiter's moons are a cosmic jigsaw puzzle, each piece telling a different story about the planet's violent past. While the four largest Europa, Ganymede, and Callisto seem to have formed alongside Jupiter in a swirling disk of gas and dust, dozens of smaller, irregular moons orbit in bizarre, tilted paths that defy this orderly origin. These oddballs, some no bigger than a city block, loop around Jupiter backwards or at extreme angles, as if they were strangers crashing a family reunion. The question is, did Jupiter steal these moons from the depths of space, or is there a deeper mystery hidden in their chaotic dances? The case for captured asteroids is strong. Unlike the large spherical moons that orbit neatly along Jupiter's equator, irregular moons like Himalaya, Carm, and Pasiphae follow wild, elongated paths, often moving in the opposite direction of Jupiter's rotation. This retrograde motion is a dead giveaway. It's incredibly unlikely these objects formed in place, since a protoplanetary disk would have lined them up with Jupiter's spin. Instead, they look like survivors of a cosmic heist, snatched by Jupiter's gravity as they wandered too close. Supporting this, many share chemical similarities with asteroids from the outer solar system, particularly the Trojan and Hilda groups, suggesting they were once free-roaming nomads before Jupiter claimed them. But here's the twist: capturing a moon isn't as simple as it sounds. For gravity to steal a passing asteroid, something has to slow it down, otherwise, it would just whip around Jupiter and escape. One theory suggests young Jupiter's extended atmosphere, puffy and thick during its formation, acted like a dragnet, sapping energy from intruders until they were trapped. Another idea points to collisions. If two asteroids smash together near Jupiter, the debris might have been moving slowly enough to get caught. Some models even propose a three-body tango, where a close encounter with another giant planet, like Saturn, knocked asteroids into Jupiter's grasp during the solar system's chaotic youth. Yet not all irregular moons fit the capture story. Some, like Themisto, orbit in a strange middle ground, neither neatly aligned nor fully wild. Their paths hint at a hybrid origin. Perhaps they formed from debris left over after Jupiter's main moons coalesced, or were once part of larger objects that shattered in ancient collisions. The real enigma is Valetudo, a tiny moon discovered in 2018. It orbits prograde in the same direction as Jupiter's spin, but crosses the paths of retrograde moons like a salmon swimming upstream. This cosmic daredevil shouldn't last long. Sooner or later, it's likely to collide with one of its backward-moving neighbors, scattering fresh debris into Jupiter's gravity well. The debate isn't just academic. If most irregular moons are captured, they're time capsules from the early solar system, preserving materials that Jupiter's violent growth might have otherwise scattered. But if some formed in place, they could reveal hidden chapters in Jupiter's history, like lost siblings of the Galilean moons. Every new discovery, like the 22 irregular moons spotted in 2018, adds another layer to the puzzle. One thing's clear: Jupiter didn't just build its moon system, it fought for it, claimed it and maybe even stitched it together from the wreckage of a younger, wilder solar system. On June 30, 1908, a fireball brighter than the sun tore through the skies above Siberia, leveling 800 square miles of forest in a blast equivalent to 12 megatons of TNT. The Tunguska event remains the largest impact in recorded history, yet no crater was ever found. For over a century, scientists assumed a rogue asteroid or comet fragment was to blame. But a radical theory suggests the cosmic culprit didn't come from deep space at all. It might have been thrown our way by Jupiter's gravity, turning the solar system's largest planet into an unwitting cosmic sniper. The idea hinges on Jupiter's role as the solar system's gravitational bouncer. Its immense mass acts like a lens, bending the paths of comets and asteroids that wander too close. Most end up ejected into interstellar space or swallowed by Jupiter itself, but a few could get redirected toward the inner solar system like billiard balls. Computer simulations show that a comet fragment drifting near Jupiter's orbital path could have been slingshotted toward Earth in the early 20th century, arriving with just the right trajectory to explain Tunguska's high-speed, shallow-angle impact. The telltale signature, such a comet would likely have been a fragile, ice-rich body, explaining why it disintegrated in the atmosphere instead of punching a crater into Siberia's permafrost. Critics argue the odds are astronomically low. Jupiter's gravitational deflections are chaotic, making precise predictions nearly impossible. Worse, no telescope spotted a comet approaching Earth around 1908, though records from that era were spotty. But proponents counter that Jupiter's handprint might still be visible in Tunguska's aftermath. The blast pattern suggests the object came from the northwest, a direction matching the orbit of Jupiter's torrid meteor stream, a debris cloud left by a giant comet that fragmented thousands of years ago. If a torrid fragment got nudged by Jupiter's gravity, it could have become a cosmic bullet with Earth's name on it. The implications are chilling. If Jupiter occasionally flings debris our way, it means the gas giant isn't just protecting Earth by swallowing threats, it might also be silently arming them. Current planetary defense efforts focus on tracking near-Earth asteroids, but Jupiter's scattered comets could arrive with little warning, moving too fast for interception. The torrid stream alone contains millions of potential hazards, some miles wide. A future Tunguska-scale object hitting a populated area could devastate a city, and the larger fragments lurking in the stream could trigger global catastrophes. Whether or not Jupiter played a role in 1808, the scenario forces us to rethink planetary defense. Telescopes like the upcoming Vera C. Rubin Observatory will scan for faint, fast-moving objects that might be Jupiter's celestial handiwork. Meanwhile, missions like NASA DART prove we can alter an asteroid's path, but stopping a Jupiter-driven comet might require intercepting it far earlier, before it barrels into the inner solar system. The Tunguska mystery serves as a sobering reminder. In the cosmic shooting gallery we call the solar system, Jupiter isn't just a shield, sometimes it might be the slingshot. Jupiter looms in our solar system like a cosmic guardian, or perhaps a celestial sniper. For decades, astronomers have debated whether its massive gravity protects Earth from devastating comet impacts, or subtly steers them toward us. The idea that Jupiter acts as a cosmic vacuum cleaner, sucking up dangerous debris before it reaches the inner solar system, gained traction in the 1990s. Simulations showed its gravity deflecting long-period comets, those wandering in from deep space, either capturing them or hurling them out of the solar system entirely. Without Jupiter, some estimates suggest Earth might face impact events up to 1,000 times more frequently, but newer research paints a more complicated picture, revealing Jupiter's role as both protector and provocateur. Take the case of comet Shoemaker-Levy 9. In 1994, astronomers watched as Jupiter's gravity ripped the comet apart, pulling its fragments into a collision course with the planet itself. The resulting fireballs, some larger than Earth, scarred Jupiter's atmosphere for months. This event seemed to confirm Jupiter's protective role, a celestial bodyguard taking the hit so we wouldn't have to. Yet other studies suggest Jupiter's influence isn't so one-sided. The same gravitational pull that intercepts incoming comets can also perturb objects from the Kuiper belt or Oort cloud, nudging them onto paths that cross Earth's orbit. It's like a bouncer who occasionally tosses a rowdy patron straight into the crowd. The controversy centers on Jupiter's dual nature. On one hand, its gravity creates a ejection lane, flinging unstable comets into interstellar space before they reach us. Researchers at NASA Jet Propulsion Laboratory calculated that without Jupiter, Earth would experience 3 times as many collisions with long-period comets. On the other hand, Jupiter's immense bulk stirs up the asteroid belt, increasing the chances of debris being nudged inward. Some simulations even suggest Jupiter's gravity can pump up the eccentricity of near-Earth asteroids over millennia, turning harmless rocks into potential threats. The Taurid meteor stream offers a chilling real-world example. This ribbon of debris, remnants of a giant comet that broke apart 20 to 30,000 years ago, intersects Earth's orbit and includes fragments large enough to cause regional devastation. Some scientists argue Jupiter's gravity helped shape the stream and may still be shepherding dangerous chunks toward us. The Tunguska event of 1908, a mystery blast that flattened Siberian forests, has been linked to a Taurid fragment, raising the unsettling possibility that Jupiter played an indirect role in one of Earth's most powerful modern impacts. So is Jupiter our shield or our saboteur? The answer might depend on timescales. Over millions of years, Jupiter likely prevents more catastrophes than it causes. But in the shorter term, its gravitational nudges could be loading the cosmic gun. The debate isn't just academic, it shapes how we track near-Earth objects. If Jupiter's influence is net protective, we might focus on local asteroid detection. If it's a chaotic catalyst, we'd need deeper surveys of the outer solar system to spot Jupiter-influenced threats earlier. For now, one thing's clear: Jupiter's role in Earth safety is as complex as its storm-racked atmosphere, a reminder that in the gravitational web of the solar system, nothing is ever as simple as it seems. For nearly a century, Jupiter's southern hemisphere hosted a trio of enormous white ovals, anticyclonic storms, so stable they earned names like BC, De, and Fa. These swirling tempests, each larger than Earth, marched in formation across the planet's cloud tops, seemingly permanent fixtures in Jupiter's chaotic atmosphere. Then in the late 1990s, something unexpected happened. 2 of the ovals began drifting toward each other, merging in a slow-motion collision that defied every expectation about how planetary storms behave. By 2018, the last remaining oval had been absorbed by the Great Red Spot itself, leaving scientists scrambling to explain why some of Jupiter's mightiest storms vanish while others, like the iconic red spot, endure for centuries. The merger wasn't just a celestial spectacle, it revealed fundamental gaps in our understanding of fluid dynamics on planetary scales. Earth's hurricanes dissipate within days when they hit land or cold water, but Jupiter's storms have no solid surface to sap their energy. The white oval should have persisted indefinitely, fueled by heat welling up from Jupiter's interior. Instead, when oval BC approached D in 1998, the 2 vortices began a months-long dance, circling each other like sumo wrestlers before finally combining into a single, larger storm. Infrared observations showed the merged oval digging deeper into Jupiter's atmosphere than either storm had alone, as if the collision had supercharged its roots. This hinted at a possible survival strategy. On Jupiter, storms might need to cannibalize each other to tap into deeper energy reserves. That theory gained weight in 2017, when the last survivor, now dubbed Oval B, drifted too close to the Great Red Spot. Unlike Earth's weather systems, which repel each other like magnets, Jupiter's vortices appear to follow stranger rules. Rather than bouncing apart, Oval B stretched, its western flank drawn into the red spot's grasp like taffy. Over months, the smaller storm was pulled apart, its identity erased as the red spot grew slightly larger and redder, possibly enriched by chemicals dredged up from oval Ba's depths. Hubble images captured the moment with eerie clarity, one of Jupiter's most enduring features absorbing a storm nearly its own size without missing a beat. What separates ephemeral storms from eternal ones? The answer might lie in the Great Red Spot's unique vertical structure. While the white ovals were relatively shallow, the red spot appears to be a towering vortex, possibly extending over 200 miles downward into Jupiter's atmosphere. This depth could act like an anchor, stabilizing the storm against disruptions that would shred smaller systems. Another clue comes from the spot's color changes post-merger. Its intensified redness suggests it's drawing material from layers where complex molecules like ammonium hydrosulfide form, giving it access to chemistry the white ovals couldn't reach. The implications stretch beyond Jupiter. If merging is key to storm longevity, it could explain why gas giants like Saturn host short-lived white storms while Jupiter's Great Red Spot reigns supreme. Perhaps longevity isn't about initial size, but about a storm's ability to consume rivals and grow deep roots. As astronomers study exoplanets with violent weather, Jupiter's vanished ovals serve as a reminder. Even the mightiest storms must adapt or perish in the endless churn of a giant planet's atmosphere. Their disappearance wasn't an ending, it was a lesson written in wind and cloud, teaching us that on Jupiter, survival favors the hungry. While Jupiter's Great Red Spot commands attention, the planet's southern hemisphere hides an equally mesmerizing spectacle, a flawless string of smaller storms known as the String of Pearls. These 8 or 9 swirling ovals, each comparable in size to Earth's largest hurricanes, line up with eerie precision along a jet stream like jewels on a cosmic necklace. Their uniformity is so striking it seems almost artificial, as if some unseen hand arranged them at perfect intervals, but the real mystery isn't just their spacing, it's why these storms refuse to collide or merge, despite orbiting a planet where atmospheric chaos reigns supreme. The pearls owe their symmetry to Jupiter's powerful jet streams, which act like atmospheric conveyor belts. These high-speed winds, blowing eastward at nearly 300 miles per hour, carve out stable lanes where storms can form and persist. Unlike Earth's hurricanes, which drift unpredictably, the pearls remain locked in place by the jet stream's momentum, like boats anchored in a raging river. Yet that doesn't fully explain their even distribution. Some scientists believe planetary-scale waves, pulsing through Jupiter's atmosphere, create zones of alternating high and low pressure, effectively marking off parking spaces where storms can thrive without encroaching on their neighbors. It's a self-regulating system where the storms themselves might generate the conditions that keep them apart. What's even stranger is how long-lived these pearls are. First spotted by Voyager in 1879, they've maintained their formation for over 4 decades, with individual storms lasting longer than most human lifetimes. On a planet where turbulence reshapes cloud features within days, this stability borders on miraculous, but cracks in the pattern are starting to show. In 2017, one of the pearls suddenly darkened, its bright white clouds turning a deep reddish-brown, a sign it might be drawing up material from deeper, hotter layers of the atmosphere. Then in 2020, 2 pearls began oscillating toward each other, sparking speculation that a merger could be imminent. If that happens, it could trigger a chain reaction, destabilizing the entire string. The fate of the pearls might mirror Jupiter's other enigmatic storms. Just as the Great Red Spot consumes smaller vortices to sustain itself, these ovals could eventually collide, forming a larger storm system. Or they might simply fade, their energy gradually sapped by the same atmospheric waves that birthed them. Every observation from spacecraft like Juno adds another piece to the puzzle, revealing subtle interactions between the pearls and their environment. What makes this string of storms so captivating isn't just their beauty, it's the way they defy expectations. In a universe where chaos is the norm, Jupiter's pearls are a rare example of order emerging from turbulence. Whether they endure or unravel, they'll continue to teach us how giant planets choreograph their storms, and perhaps even how similar patterns emerge on exoplanets light years away. Their existence is a reminder that even in the most violent atmospheres, nature sometimes finds a way to string together perfection. Deep within the invisible reaches of Jupiter's magnetosphere, a cosmic symphony crackles to life, not with melodies, but with bursts of radio noise so bizarre they've been compared to lasers, whales singing, or even the otherworldly chatter of a sci-fi transmission. These aren't random static, they're structured rhythmic emissions pulsing with such precision they sound like nature's own radio station. For decades, scientists have strained to decode these eerie signals, uncovering a hidden language of charged particles trapped in Jupiter's magnetic grip. The closer we listen, the stranger the story becomes. The primary culprit behind these sounds, Jupiter's volcanic moon Io. As Io spews sulfur dioxide into space, Jupiter's magnetic field rips apart these molecules, creating a donut-shaped plasma torus along the moon's orbit. Electrons whip to near light-speed spiral along magnetic field lines, releasing energy as radio waves in a process called cyclotron maser instability. Think of it like a cosmic particle accelerator, except instead of generating light, it broadcasts pulses across the solar system. The result, a eerie chorus of decametric radio emissions, detectable by Earth-based antennas when Jupiter's rotation aligns just right. But there's a rhythmic twist. These radio bursts follow strict cycles, flaring predictably every few hours. The pattern matches Io's orbital dance. Every 42 hours, the moon's movement through Jupiter's tilted magnetic field triggers a surge of fresh particles, amplifying the emissions like clockwork. It's a celestial metronome, ticking with precision that rivals atomic clocks, yet even within this regularity, surprises lurk. Sometimes the radio lasers split into dual frequencies, suggesting hidden structures in Jupiter's magnetosphere. Other times they vanish entirely for days, as if a cosmic hand flipped a switch. The most haunting variations come from Jupiter's poles. Here, the radio noise morphs into something darker, shrieks and howls created by electrons crashing into the upper atmosphere. NASA Juno spacecraft recorded these sounds during close passes, revealing bursts so powerful they can outshine the sun in radio wavelengths. Unlike the Io-linked pulses, these emissions seem tied to Jupiter's internal magnetic chaos, flaring unpredictably like a storm-lashed lighthouse. What makes these radio mysteries more than just cosmic static? They're a direct line into Jupiter's invisible forces. By tuning into these frequencies, we've mapped the planet's magnetic field in ways optical telescopes never could, uncovering its wild asymmetries and hidden currents. Future missions might even use them to probe the oceans of Europa or Ganymede, whose conductive saltwater could subtly distort Jupiter's radio whispers. Every burst, every silent gap, carries encrypted clues about the chaotic, beautiful machine that is Jupiter, a reminder that sometimes the universe speaks in frequencies we're only beginning to hear. In July 2020, astronomers training their telescopes on Jupiter witnessed something unprecedented, a shadowy maelstrom materializing almost overnight in the planet's northern hemisphere. This wasn't just another storm. The vortex was a deep, inky black, standing out starkly against Jupiter's pastel-colored cloud bands like a hole punched through the atmosphere. Dark spots aren't unheard of in the solar system. Neptune famously sports its own great dark spot, but Jupiter's version emerged with startling speed, leaving scientists scrambling to explain why a planet known for its slow-evolving weather patterns suddenly birthed such a stark anomaly. The vortex's abrupt appearance challenges everything we thought we knew about gas giant storms. Jupiter's most famous tempests, like the Great Red Spot, evolve over centuries, their cycles measured in decades, not days. Yet this dark spot, officially dubbed NLRS-1, it popped into existence with the suddenness of a lightning strike. Infrared imaging revealed it wasn't just a surface feature. The vortex plunged deep into Jupiter's atmosphere, possibly rooted in layers where pressures crush gases into exotic forms. Its darkness suggested high-altitude particles absorbing sunlight rather than reflecting it, perhaps hydrocarbon hazes or phosphorus compounds dredged up from lower altitudes. But what force could yank such material upward so violently? Comparisons to Neptune's dark spots only deepen the puzzle. Neptune's storms are thought to be methane-clearing vortices, where swirling winds expose darker layers below. They're also transient, with the original Great Dark Spot spotted by Voyager 2 in 1989, vanishing by the time Hubble looked in 1994. Jupiter's dark vortex, however, appeared in a completely different atmospheric regime, colder, richer in ammonia, and lacking Neptune's methane-dominated chemistry. Yet both planets share one eerie similarity: their dark spots seem to emerge from nowhere, as if some hidden atmospheric switch flips without warning. Theories about Jupiter's dark vortex range from the plausible to the provocative. One camp argues it's a rare anticyclone, a high-pressure storm where sinking gases suppress cloud formation, creating a clear window into Jupiter's darker depths. Others propose it's the opposite, an upwelling so violent it ripped apart overlying cloud decks, exposing shadowy materials beneath, the wildcard theory. Electromagnetic effects, where Jupiter's lopsided magnetic field somehow triggered a localized atmospheric collapse. Supporting this, Juno's magnetometer detected unusual fluctuations near the vortex's latitude around the time of its formation. What makes this event more than just a celestial curiosity is the timing. The dark vortex appeared during a period of unusual atmospheric calm, right as Jupiter's trademark jet streams showed unexpected weakening. Some researchers speculate the spot might be a symptom of larger shifts in Jupiter's climate, a visible tip of hidden changes roiling beneath the clouds. Unlike Neptune's spots, which come and go like weather fronts, Jupiter's dark vortex could be a barometer for deeper, planet-wide transitions we're only beginning to detect. As telescopes continue to monitor its evolution, one thing's certain: this ink-eye scar on Jupiter's face is more than a storm, it's a signal, broadcasting secrets about the unseen forces rewriting the rules of planetary weather. Jupiter isn't just a planet, it's a cosmic paradox, from its shrinking great red spot to its lopsided magnetic field, from the missing core that shouldn't exist to the hexagonal storms that look like they were drawn with a ruler. Every discovery we make seems to defy the rules we thought governed gas giants. Even its most familiar features, like lightning and auroras, behave in ways that leave scientists reeling. The deeper we look, the clearer it becomes: Jupiter doesn't follow the playbook. It writes its own. Consider the contradictions. A planet that should be soaking wet has deserts in its clouds. A storm that's raged for centuries might now be fading before our eyes. Moons that should be frozen dead worlds hide oceans larger than Earth's, while others spew lava into space like geysers of molten rock. And let's not forget the radio whispers, those eerie, pulsing signals that sound like a transmission from some alien intelligence, only to be the natural static of charged particles trapped in Jupiter's magnetic grip. Each mystery peels back another layer, revealing just how little we truly understand about this titan of our solar system. The good news: our quest to unravel these puzzles is far from over. Missions like NASA Europa Clipper and ESA's JUICE are set to launch soon, armed with instruments that could finally answer whether life swims in the dark oceans beneath Europa's ice or Ganymede's hidden seas. Future probes might even dare to dive deeper into Jupiter's storm-racked atmosphere, sniffing out the secrets of its missing water or the bizarre metallic hydrogen lurking beneath the clouds. And let's not forget the James Webb Space Telescope, already turning its infrared gaze toward Jupiter's swirling poles, searching for clues in the heat signatures of its most enigmatic storms. So here's the real question: which of Jupiter's mysteries fascinates you the most? Is it the great red spot's slow fade, or the way lightning crackles without rain? Maybe it's the thought of Europa's hidden ocean, or the eerie geometry of those polar cyclones. Drop your thoughts in the comments. We'd love to hear which cosmic riddle keeps you up at night. And stay tuned, because with every mission, every telescope observation, we're inching closer to uncovering the truth behind Jupiter's greatest secrets. One thing's certain, the next chapter in this story promises to be even more surprising than the last.